Okay, in this video we're going to start looking at Chapter 5, differential equations here. And we're going to do the first three sections in this course, 5.1, slope fields and Euler's method. Well, this video we're going to start slope fields. We do not do Euler's method. It is not on the AP test. From 5.2, we'll do the growth and decay. And then 5.3, we'll do the first few examples from this. The section's called separation of variables, and that's as far as you have to go on the AP test as far as differential equations are concerned. So again, we're just going to keep to what you might see on the AP test. 5.4, logistic equation, we will not see that at all. Okay, the assignment for 5.1, the slope field section, there's only one problem in the textbook, problem 2 on page 373. The rest of the assignment will be on WebAssign. And here we are in section 5.1, slope fields. Again, we're not going to do Euler's method. It says here we're going to use initial conditions to find particular solutions of differential equations. We'll use slope fields to determine approximate solutions of differential equations. And then again, Euler's method. It's an approximation method, and it's not tested on the AP test, not on the AB test. So we're not going to look at that in this class. And the book goes on to say, in this text, you're going to learn different physical phenomena can be described by differential equations. Recall that a differential equation in x and in y is an equation that involves an x and a y and the derivatives of y. For example, here we got a 2x times y prime minus 3y equals 0. It has x's, it has y's, it even has a y prime in it. So that's a differential equation. In the next section, you'll see that problems involving radioactive decay, population growth, and Newton's law of cooling can be formulated in terms of differential equations. So a function, y equals f of x, is called a solution of a differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. For example, differentiation and substitution would show that this, y equals e to the negative 2x power, is a solution of this differential equation, y prime plus 2y equals 0. So what we'd do there, we would take the derivative of y and then plug it in for y prime, and then we'd do 2 times this y, and it would in fact equal 0. And it can be shown that every solution of this differential equation is of the form this, y equals ce to the negative 2x, where that c, the constant, is any real number. This solution is called the general solution. Remember, that has the c in it, the constant. Some differential equations have singular solutions that cannot be written as special cases of the general. Such solutions, however, are not considered in this text. The order of a differential equation is determined by the highest order derivative in that equation. For instance, y prime equals 4y. That's a first order differential equation because it's the first derivative of y. Back in Chapter 4, Section 1, Example 9, we saw a second order differential equation. The second derivative, s double prime of t equals negative 32, had this general solution. Remember, this here would be the acceleration. We would antiderive that to velocity, and then we would antiderive velocity to get back to position. So here's s of t, our position function, is negative 16t squared plus c sub 1, that's our first constant, times t, plus c sub 2. It can be shown that a differential equation of order n has a general solution with n arbitrary constants. Example 1. Determine whether each function is a solution to this differential equation. Y double prime minus y is equal to 0. And they give us three of them here, A, B, C. Let's look at letter A first. We've got y equals sine x. And we're going to need that second derivative to put in right here. So if y is sine x, y prime, come on, the derivative of sine is cos x. And then if we derive that again to get to y double prime, the derivative of cosine is negative sine x. So I'm going to do y prime, or excuse me, y double prime minus y. So y double prime minus y, does that equal 0? Well, this y double prime, we just found that. That is the negative sine of x. And then we're going to do minus y, that's our original function, sine of x. Does that equal 0? Well, if this was a plus here, it would. We'd have a negative sign plus sign, that would equal 0. Or if this was a positive sign minus sine x equals 0, we could combine over here and get negative 2 sine x equals 0. Now, it is possible we could solve this, and there are a couple answers of x that would make this true, but we're trying to verify it's a solution for all values of x. So here we can say no. Y equals sine x is not a solution to our given differential equation. Letter B, here's our y equals. We need to get to, again, y double prime. So if we derive that the first time, we're going to need a chain rule. 4e to the negative x is going to derive to itself 4e to the negative x, but we have a negative x up here. The derivative of that would be negative 1, so we would multiply by a negative 1. And now we need the second derivative, y double prime. So we derive again. This will be its own derivative, negative 4e to the negative x. But again, we'll chain rule. Negative x derives to a negative 1, so that'll change us back to a plus. So y double prime minus y, does that equal 0? Well, here's our second derivative, 4e to the negative x. And then we're going to minus our original y, and that was right here, 4e to the negative x. Does that equal 0? Yeah, we've got this, and we're subtracting the exact same thing from it. It's like 4 apples minus 4 apples is no apples. So B, yes, y equals 4e to the negative x is a solution to that given differential equation. Now for letter C, just remember that this C here is just some unknown constant. So if we derive for the first time, the derivative of ce to the x is ce to the x. We would chain rule here, but it would just be multiplying by 1, so that changes nothing. And if I derive again y double prime, that will be the same thing, ce to the x. So if I want to do y double prime here, minus the original y, ce to the x, does that equal 0? Yes, anything minus itself does equal 0. So that is a solution to the given differential equation. So there we were, verifying solutions. Geometrically, the solution, the general solution of a first-order differential equation represents a family of curves known as solution curves. We saw this when we were doing anti-deriving. One for each value assigned to that arbitrary constant. For instance, you can verify that every function in this form, y equals a constant divided by x, is a solution of this differential equation. X times the derivative of y plus y is equal to 0. Now it says here figure 5.1. I forgot to put that in the slideshow here, but you can see it in your textbook. The figure shows 4 of the solution curves representing corresponding to different values of the constant. As we discussed back in 4.1, particular solutions of a differential equation are obtained from some initial condition that give the values of the dependent variable or one of its derivatives for particular values of the independent variable. The term initial condition stems from the fact that often in problems involving time, the value of the dependent variable or one of its derivatives is known at the initial time, time 0. For instance, the second order differential equation, s double prime of t is negative 32. We would anti-derive that twice, and we could get to here. S of t is negative 16t squared plus constant 1 times time plus constant 2. It would have these following, or we might have these following initial conditions. S of 0 is 80. So we could go to this equation, put in 0 for all the t's, and get a height of 80. And s prime of 0 is 64. So the first time we anti-derive, we get constant 1 here. We could sub in 0 for t and 64, and set it equal to 64, and we would get that the c value is 64. So plugging in those initial conditions, we would have this particular solution. And in example 2, we're going to find one of these particular solutions. For this differential equation, x times y prime minus 3y equals 0, verify that this x cubed is a solution. And then after we verify that, we're going to find the particular solution determined by this initial condition. Y is 2, x is negative 3. We could look at this as a point. Negative 3 comma 2 is a point that's going to be on our particular solution curve. So let's see here. Here's our differential equation. X, y prime, minus 3y is equal to 0. Well, let's see here. X, that's just x. We'll leave it alone. We got to multiply that by the derivative of y. And I'm going to come over here and change ink to red. So we know y is equal to cx cubed. Let's derive that. Y prime. So we would derive this with the power rule. The 3 would come down front, get multiplied by c, whatever it is, and then we're going to have x to 1 power lower, x squared. So I'm going to put that in here for this y prime, 3c x squared. And then we've got this minus 3y minus 3. And then I'm going to put in this set of parentheses my y value, cx cubed. Cx cubed. Does this equal 0? So let's see, if I multiply here, I'd multiply the two base x's and get an exponent, add those exponents up and get a 3cx cubed. Minus here, if I just multiply, sort of drop the parenthesis, I get a 3cx cubed. Does that equal 0? Yeah. 3 of these minus 3 of the same things is equal to nothing. Okay, and now it says find the particular solution determined by this given initial condition. So let's go. I didn't want to erase. There we go. So back to here, y equals cx cubed. Well, here they gave us an x and a y value. If we plug those in, the only unknown left will be c. So y turns into a 2. C is what we're going to find, and x turns into a negative 3. That's supposed to be a 3. There we go. So 2 equals c. Negative 3 to the third power is negative 27. Divide both sides by the negative 27, and we get c equals negative 2/27. So here is our general solution. It's got the c value in it. And then our particular solution, would be y equals negative 2/27 x to the third power. So general has the unknown constant in it. In the particular, we use the given point, the initial condition, to solve for that c value. And what do we got down here? Note that to determine a particular solution, a number of initial conditions must match the number of constants in our general solution. And now that brings us to slope fields. And it says here, solving a differential equation analytically can be difficult or even impossible. However, there is a graphical approach that we can use to learn a lot about the solution of a differential equation. Consider a differential equation in this form. Y prime is equal to f of x comma y, where that f of x comma y is some expression in terms of x and y. At each point, xy, in the plane where f is defined, the differential equation determines the slope y prime at that given point of the solution at that point. If you draw a short line segment with that slope at that selected point in the domain of the function, these line segments will form a slope field. or a directional field for that differential equation. Each line segment has the same slope as the solution curve at that exact point. The slope field shows the general shape of all the solutions and can be helpful in getting a visual perspective of the directions of the solutions of our differential equation. And then it says here, the ability to identify, interpret, and draw a slope field is tested on both AP exams, AB and BC. Now here we're going to sketch a little slope field. The book only asks us for 3 points, so we're going to do a few more, just to have fun. Over here we've got a blank graph at -2 to 2 on the x-axis, 0 to 2 on the y. And here is our differential equation. Let me write it again over here. So y prime, the slope occurring at that point, is equal to the x-coordinate minus the y-coordinate. And then they gave us here a few points to check out. So let's do this one first, -1, 1. At -1, 1, our x-coordinate is a -1, minus our y-coordinate, which is 1. If you subtract those, you get a -2. So if I go to this point, -1, 1 is right here. Oh, and my pen's not going to, there it is. And I'm going to draw a line segment with a slope of -2. Now, -1 would be about a 45-degree angle going down. So I want to be a little steeper than that. So here I am at -1, 1, and a pretty steeply sloped, downward sloped line. All right, next point they want from us is 0, 1, 0, 1. So our x-coordinate is 0 minus our y-coordinate 1. That's a -1. So if I go to the point on my graph, 0, 1, I'm right here on the y-axis. My line will be sloped downward at a slope of -1, or about 45 degrees down. It's less steep than the last one we did. And then the book asks us for a 1, 1. So my x-coordinate's 1 minus my y-coordinate 1. That's a slope of 0. So if I go over to 1, 1, my little line segment will be horizontal or parallel to the x-axis. So that's all the book asked us to do. Let's do a few more. Again, I'm having fun. Let's do 0, 2. 0, 2. So I would go in my differential equation. X is 0 minus 2 is y. That's equal to -2. So at 0, 2 up here on the y-axis, we're going to have the same slope as this one here. Steeply downhill, slope of 2, -2. 0, 0, the origin. That'll be a nice easy one. X is 0 minus y is 0. That's equal to 0. So right on the origin, we have a little horizontal line segment. How about 1, 0? X is 1 minus y is 0. 1 minus 0 is 1. So if I go over to 1, 0, I'm uphill now, 45 degrees, or a slope of 1. And let's do one more, -1, 0. So my x-coordinate is -1 minus my y-coordinate 0. That's equal to -1. So we're going to be sloped downhill. Not as steep as above here. Same one as at the y-intercept of 1 on the y-axis. So there's our slope field. It's not very impressive with just 7 little line segments. You'll see some that have, quite a few on there. And you can sort of get an idea of the flow of the graph as it would go through that slope field or directional field. And let's take a look at some. Here's a matching exercise. Example 4. Match each slope field with its differential equation. So let me move this up here. Make it a little smaller. So let's look at our differential equations first. The first one here, the slope, y prime, is equal to the x-coordinate plus the y-coordinate. For the second one down here, the y-coordinate, or excuse me, the slope is equal to the x-coordinate. And for the third one, y prime, or the slope, is equal to the y-coordinate. So let's look at these graphs and see if we can figure an easy one out. I'm looking at letter A here, and notice all along the y-axis, all of those are horizontally sloped, 0. If I come over here, they're all very steep, parallel as I look up and down the columns. And let's look here. So this is my x-coordinate. My x-coordinate is -2. All my lines are steeply sloped. They're all the same. When I get to the y-axis, my x-coordinate is 0. All the line segments are horizontal, slope 0. Over here at +2, all my little line segments are sloped up nice and steep, looks like a slope of 2. So here it looks like my slope is equal to my x-coordinate. So it looks like this one is matched up with A. Now if we look at the last graph here, C, as I look again across, now it's the x-axis. All of them are horizontal, lying right on top of the x-axis. If I come up here to 2, y is 2, they're all steeply sloped uphill, looks like a slope of 2. If I come down here to -2, scanning across, we can see that they're all sloped downhill pretty steeply. So this, it looks like our slope is the same as our y-coordinate. As we go up, each line segment gets steeper and steeper. As we go down, they're steeper and steeper in a negative slope direction. So this one looks like C. And I guess by the process of elimination, we can look at this last one here. This would be B. But let's look at it a little bit. The x and the y coordinate add up to the slope. So look at this. -2 plus 2 is 0. -1 plus 1 is 0. 0 plus 0 is 0. 2 plus a -2 would be 0. So here when we look down this diagonal, all the slopes are the same. At least here, because it's just we're adding a positive and a negative number, the same value together. And notice they get real steep as we head out. Here would be x-coordinate 1, y 0. X-coordinate 1, y-coordinate 1, so it got steeper. X-coordinate 1, y-coordinate 2 got steeper as we go up. And it would be the opposite. As we go down, they're going to get steeper and steeper downhill. Now this example 5, this is new to the new edition. It says here a solution curve of differential equation y prime equals f of xy. Is simply a curve in that the xy plane, whose tangent line at each point has a slope equal to that value. This is illustrated here in example 5. So it wants us to sketch a slope field. We're not going to sketch it. It's provided for you in the notes. But we're going to fill in this table a little bit just to sort of go through the process. Sketch the slope field to this differential equation. Y prime, the slope at that occurring at that point, is equal to 2 times the x-coordinate plus the y-coordinate. And then we're going to use that slope field to sketch a solution that passes through this given point. So let's fill in our table. So whatever our x-coordinate is here, we're going to double it, and then we're going to add y. Double the x and add y. So if we double that, -4, add y, we get -5. Double this, -4, add 1, -3. Double this, -2 minus 1 more, also -3. Double this, -2, add 1, -1. Double the x, add the y, -1. Double the x, add the y, 1. Double the x to 2, add the y, 1. Double the x, add the y, that'll be a 3. Double this to 4, add y, -1, that would make that a 3. Double that to 4, add 1, 5. So here are some slopes occurring on our slope field. And is this it up here? Yeah. So here's what our slope field looks like. If we were to graph these line segments and a whole bunch of more, we get this slope field. So once the slope field has been created, we can sort of use it to estimate some curves. So now it says sketch the solution going through 1, 1. So let's find point 1, 1. So here's 2, halfway over would be about here. Here's 1, 1. I'm going to put a point right on that. Now what we want to do is sketch how the graph would flow through this slope field or directional field based on this point. And you could think about these little line segments as, or think of this as a gravitational field. As you get close to these little line segments, you become parallel to them, sort of like their gravity straightens you out so you're parallel to them. So if I'm here at this dot and I start by going up, I'm going to come out of here and I'm parallel to these line segments. As I keep moving up, they're all pretty much the same. I'm just going to stay parallel to the line segment I'm closest to. And there's where we'd go off the page, so we're going to stop in that direction and start heading back down. Now as I start coming down here, I'm going to bend a little bit because I'm going to try to be parallel to in between these. So I'm going to sort of look like that. And as it's steering me down here, this one's a little more straightened out. And notice all of these on the y-axis are sort of straightening out. So as I'm going to come down here, I'll become parallel to this one. As I'm working down here, I've got this one sloped down, this one sloped up, so I'm going to be in between and sort of straighten out. And now I'm getting closer to these two. I'm going to sort of become parallel to them, and my graph is getting bent back up. So now here I'm sort of parallel to these, and going to look sort of parabolic in shape. And there we go. And of course, this is an estimation method. If you're working together on a homework or a worksheet with somebody, your graph might not be exactly the same as everybody else's. Maybe somebody else's come a little lower down here, or maybe it just hit the origin. Again, this is sort of an estimation method, and everybody's interpretation is going to be a little bit different. And now here, right in the notes, if you have a TI89 calculator of your own, you can do this at home. If not, this is something we'll do in class. The TI89s can create slope fields and put initial conditions in and graph them. I stole this out of a different book somewhere or an online lesson plan. So if you just follow along the directions exactly as you read them, you'll see here, if you go through the directions, you will create a slope field. And then it will go back to the directions. It'll give you how to put in an initial condition, and then the graph will plot that point. And then it's real neat to see it'll slowly draw the function going through your slope field. So if you don't have a TI89 at home, that's something we'll do in class. And that's where I'm going to end this video. The examples are over. I will make another video. Here we're going to do some odd problems that are adjacent to the even problems, kind of like the ones you'll see on the WebAssign.